Hello everyone, today we're going to be going over the entire short answer section of the June 2019 Physics Regents exam. This is part B-2. If you want to look at the multiple choice review of this section, that is the video that I uploaded right before this. But that being said, let's just get into this. For 51, it gives us this little pretext. It says a toy launcher that is used to launch small plastic spheres horizontally contains a spring with a spring constant of 50 newtons per meter. The spring is compressed a distance of 0.10 meters when the launcher is ready to launch the plastic sphere. Determine the elastic potential energy, right? So that's PES, right? That's stored in the spring when the launcher is ready to launch the plastic sphere. All you have to do is just plug this into the potential energy for the spring formula, right? So if you go right here, scroll down to mechanics, we're gonna get potential energy is equal to 1/2 kx squared, right? So PES, or the potential energy of a spring, is equal to 1/2 kx squared, right? So right here we have our k, we have our x. Now an important thing about this problem is it says determine, right? It says determine, and whenever it says determine, you don't need to show work, right? You do not need to show work. So all you can do is just plug this into your calculator. You need to write anything down. Plug into your calculator. You get 0.25 joules, and on your physics reference table, which I'm going to be filling out along this video, right? If you go here, 51 is literally just going to ask you to write down your answer. That's it. There's no space for your work. There's no space that they give you other than just your answer, right? And that's because whenever you see determine, all it's asking you is just tell me, right? It's not telling me how you did it. It's not telling me show your work alongside it. Just literally saying tell me what it is, right? Anyways, whenever you have, it'll tell you whenever you need to show work. Like with questions 22 and 53, it says the spring is released and a 0.10 kilogram plastic sphere is fired from the launcher. Calculate the maximum speed with which the plastic sphere will be launched. Neglect friction, show all work, right? It tells you show all work, including the equation and substitution with units, right? So here, what it's asking us is what it's giving us, right? It's giving us a mass, which is 0.10 kilograms, right? And it's asking us for its velocity. And we're going to base this question off of our previous question, right? This is these are all relating to the same question, which means that we're going to have to use some component of the previous question. In this case, right, we have mass, and we're trying to find velocity, right? What we also know is the energy of the system, right? Potential energy of the spring, right? That's going to be the total energy of the entire system, right? So we also know that the energy, right? We don't know what kind of energy, but we know that this entire system has 0.25 joules of energy in it, right? So let's look at our reference table and let's see if there's any formula that we can possibly use, right? That gives us velocity in terms of our mass and our energies. Our system's energy, right? Obviously, that's going to be our kinetic energy formula, Ke, right, which is the energy of the system, the kinetic energy of the system, right, which means that the energy of the moving system, right? We know this is going to use kinetic energy because it's being launched, right? If you're launching, you're flying. If you're flying, you're moving. If you're moving, that's kinetic energy, right? So the kinetic energy is equal to 1/2 mv squared, right? Does this use everything that's given? Well, we're using our joules, or the energy of our system from our previous question, right? And then we're using our mass that's given to us and our velocity that we're trying to solve. So yes, right? So on the real test, what you're going to do is you're going to use this formula. It says show all work, including the equation and substitution with units. You're gonna go here and you're going to write that formula down. Ke is equal to 1/2 mv squared, right? That's your formula, right? Now, if you want to be extra safe, I'm pretty sure this is good practice, but just you can also rewrite your formula in terms of the unit that you're trying to solve for, right? So just if you're worried and you want to play it safe, I would suggest just, your teacher may have told you a different thing, but if you want to be really safe, just write down your formula in terms of the thing that you're trying to solve for. Right now I'm trying to solve for v, so I'm going to write this in terms of v, right? So I'm going to write v is equal to Ke divided by 1/2 m. Right, this is v this is this formula, right, just in terms of v, right? And now that I have it in terms of v, the next step and one of the last steps I have to do is just plug in my units. I'm going to leave v blank, right, but I'm just going to plug in my units or plug in my terms, right? So I'm going to have 0.25 joules divided by 1/2 times the mass, which is times 0.10 kilograms. And this is it, right? This is the substitution with units. Always include units. If you don't include units, you're going to have points taken off, right? Plug this into your calculator. You get V is equal to 2.24 meters per second. That's your answer, right? So now we're going to go ahead. We're going to move on to number 54. It says two 10 ohm resistors have an equivalent resistance of 5 ohms when connected in an electric circuit with the source of potential difference. Using the circuit symbols found in your reference table, draw a diagram for the circuit. Well, the first and main thing I need to ask myself is this a parallel or is this a series circuit? Right? Obviously, it's going to be a parallel circuit. Why? Because if I look here, if I go up to my to where I have my electricity reference table, with series circuits, the equivalent resistance or the total resistance is equal to R1 plus R2, right? If I look here at my problem, it's saying that two 10 ohm resistance have an equivalent resistance of 5 ohms, right? So is 5 ohms equal to 10 ohm plus 10 ohms? No, that's wrong. 5 ohms isn't equal to 20 ohms, so it has to be a parallel circuit. Is 1 over 5 ohms equal to 1 over 10 ohms plus 1 over 10 ohms, right? If we solve for that 5, yes, that is going to be equal to that. That's going to be 2 over 10 ohms, which is equal to 1 over 5 ohms, right? So I know this is going to be a parallel circuit. So the next thing that I'm going to have to do is literally just go into my go into my answer sheet, and I'm just going to have to draw this circuit out, right? Now, it's saying that it has a source of potential difference, which is the same thing as saying a battery, right? So I'm going to go ahead, I'm going to draw my battery, which is going to look something like this. So that's my battery, and then connecting this battery, right, it's going to go outwards. And the thing with the parallel circuit, right, is there's usually connected along the inside, right? So here, I'm going to draw my resistor, and then here I'm also going to draw my resistor. And this is pretty much enough to get full points on this problem. Just remember that when you're drawing this, make sure that these are all at like 90-degree angles, right? Because wires can only be connected at 90-degree angles on the Regents test, right? So that is pretty much what it looks like. Make sure to label these 10 ohm and 10 ohms, and that's it. That's all you need to do for this problem, right? So number 55 says that the graph below shows the relationship between distance d and time t for a moving object. On the axis in your answer booklet, sketch the general shape for a graph that shows the relationship between the magnitude of velocity and time for the moving object, right? So I know that v is equal to d over t, right? And that this graph shows the relationship between distance and time for a moving object, which means that this slope, or the slope of this, is equal to v, right? This is d, which is our y, over t, which is our x, y over x, d over t. The slope of this is going to be my velocity, right? And when I have a constant velocity, and the thing is, this is a straight line, so this is going to have to be a constant velocity, right? The distance is increasing consistently with time, right? And if I have a just all I need to know here is that because this line is straight, I have a constant velocity. Right? Now on my reference on my table, it's asking us, using this relationship, using this graph, what is that v in terms of t? Well, if I just said that my velocity is constant, it should just be a straight line, right? Because my velocity doesn't change. If my velocity doesn't change, right, that means I'm increasing by the same amount of distance by the same amount of time. For example, if my velocity was like 5 meters per second, right, that means that every second I'm increasing by 5, right? Every second I'm increasing by 5. This is going to be a straight line because each one of these is just increasing by 5 over each interval. It's the same, right? And here, if this is my velocity, if this is 5, and it's just staying the same, right? That means that no matter what the time is, my velocity is always going to be 5 meters per second, right? So it's just a straight flat line. Moving on to number 56. It says that a ray of monochromatic light, whatever, passes from medium X into air, right? So this is medium X into air. The angle of incidence in the ray is 25 degrees as shown below. Using a protractor, measure and record the angle of refraction in the air to the nearest degree, right? So I have no way of like putting a protractor on the screen and showing y'all, but if I were to do this, remember that the angle of refraction is going to be between the incident ray or the ray and the normal. It's always going to be between the normal. It's not going to be this, never going to be that, right? It's always going to be that, right? So when you put your protractor on here, it's going to look it's really janky, but it's going to look something like that, right? There's going to be a protractor, right? And you're going to have to align it onto this line, and you're just going to have to read it. And I already did this on a separate sheet of paper that I'm just referencing. From what it seems to me, this angle is going to be 40 degrees, right? And all you have to do is just write down 40 degrees and move on, right? This is going to be 40. It's going to pass through the line that says 40. That's all, right? So you would just position it, make sure your center is on here, right? So now you know that the angle of refraction is 40 degrees. You can go ahead and solve 57 to 58. It says calculate, which means that we have to include the equation and substitution with units. It says calculate the absolute index of refraction for medium x, right? So what's given here? Right, we know with air, right? If we go into our reference table, we know that with air, the index of refraction is going to be obviously 1. So we know n. We know the index of refraction for one of them, right? And we know the angle of incidence, which is 25, and we know the angle of refraction, which is 40 degrees, right? And we're trying to find n2, or the index of, or sorry, we're trying to find n1, which is the index of refraction, right? And this sounds a lot like the formula on your reference table for waves. If you go there, it sounds a lot like the formula n1 sine theta 1 is equal to n2 sine theta 2, right? Or the index of refraction for the first one times the angle of incidence is equal to the angle of refraction. Sorry, is equal to the what's it called? The index of refraction for the second medium times the angle of refraction in the second medium, right? So if I'm trying to solve for n1, which is our first medium, or medium x, I'm just going to rewrite this formula in terms of n. And if all I have to do is just divide by sine theta 1, right? I'm going to be left with n1 is equal to n2 sine theta 2 divided by sine theta 1. Right, and all I have to do now is literally just substitution with units and then just solve, right? So here I have 1 sine 40 degrees, right? Because the index of refraction for air, which is the second medium, right? The second medium is going to be 1, right? We know that from our table, and this is going to be divided by our sine of our first angle, right? Our angle of incidence, which is sine of 25 degrees, and right, and if you actually execute this, you get n of n1 is equal to 1.52, right? That's our index of refraction. There's no there is no unit associated with that. Moving on to 59 through 60, it says a student wishes to record a 7.5 kilogram watermelon slice colliding with the ground. Calculate how far the watermelon must fall freely from rest so that it'd be traveling at 29 meters per second the instant it hits the ground, right? So what's given to me, right? A mass is given to me, right? They're asking us for distance. We know that it falls freely from rest, so we know that our v initial is 0, right? We know it's asking us, or it gives us a vf of 29 meters per second, and we know that it's accelerating, right? By gravity, right? Because it's just free fall, right? If something is freely falling, it's accelerating by gravity, right? Right, and we're trying to solve for d. So which formula would give us a, or give us d in terms of vi, vf, and a, right? Well, obviously, the formula vf squared is equal to vi squared plus 2ad will give us that, right? And just to be extra safe, I'm going to write this in terms of d, right? Which is good, just good humor. I think you all should do that, right? Just rewrite your formula in terms of whatever you're solving for. Here I have d is equal to vf squared minus vi squared over 2a, right? And then just substitute with units. We know that our final velocity that we're trying to solve for is 29 meters per second. We're going to have to square that, minus our initial velocity, which is 0 meters per second squared. And we're going to have to divide all of this by 2 times 9.81 meters per second squared. That's all. And if you plug it into your calculator, you get the distance that the watermelon has to fall to get that speed is 42.7 meters, right? So moving on to number 61 through 62, right? What did they ask us? It says that as represented in the diagram below, block A with a mass of 100 grams slides to the right at 4 meters per second and hits the stationary block B with a mass of 150 grams. After the collision, block B slides to the right and block A rebounds to the left at 15 meters per second, right? It's saying that base your answers to 63 to 65 on this question, whatever. So, wait, I'm so confused. I actually here I hate the way that they format this right, because I think that the next question is what it's actually asking me is down here, but here it's saying that calculate the speed of block B after the collision, right? So right here what we're dealing with is they give me M and they give me V, right? They give me M, they give me V, they give me M, they give me V, they give me M, and now they're asking me for V, right? And I have MV so many times, I'm going to start thinking about momentum, right? Because P equals mv, momentum is equal to mv. But I'm going to think about a very specific formula located in my reference table. It's going to say that P before is equal to P after, right? So in my space, I'm going to go start right. I'm going to write P before is equal to P after. What that means is that the momentum system, right? This is a system. The momentum on the left side, which includes the momentum of block A plus block B, is equal to the momentum of block A and block B after their collision, right? So really, what I'm going to have to write down is MA, massive A, times MA before, right, plus MB, the mass of block B, times the velocity, the velocity of block B before is equal to the mass of block A times the velocity of block A after, plus the mass of block B times the velocity of block B after, right? And I could just put these in parentheses to make this a bit more clear, right? Literally, all I'm saying is that P before is equal to P after, right? So if you add MA times MV, which is what velocity is, of both sides, they're going to equal both sides. That's all. Now all you have to do is just put this in terms of V, right? B after, or the velocity of block B after, using this formula, and you're going to get MA times VA before plus MB times VB before minus MA VA after, and you're going to just divide all of this by the mass of block B, right? Now, I'm just going to save some time. All you're going to have to do is just plug in your units, right? Plug in all of your values. Remember that this is in grams, so do not get confused. You need this in kilograms, right? Kilograms is the only accepted unit for mass, right? If you're confused on how to convert that, just divide it by 1,000, right? So if you plug in your units, plug in your values, which you need to do, you absolutely need to plug in your values. I'm just kind of too lazy to do this, and I want to save some time. You should get V. The velocity of block B after is going to have to equal to 3.7 meters per second. That's all, right? So moving on to number 36 to 64, it says, this weight of a car is traveling east at 25 meters per second. After the brakes are applied, the car is brought to rest in 5 seconds, right? It's saying calculate the magnitude of the total impulse applied to the car to bring it to rest. So we're going to have to find that value, right? So here we're talking about impulse, right? Total impulse. And right here on my physics reference table, that's represented by simple J, right? So my impulse is equal to F net times T, which is equal to the change in P, or change in momentum. I think that the easiest way to do this is just using the F net times T, right? So here, I'm going to use J is equal to F net times T. Why am I going to use that? Because it's saying that it was traveling, right? Or rather, I'm going to use this, right? I'm going to use delta P, right? So J is equal to the change in momentum, right? Which means that the impulse is going to equal to M2 or M V final, m times v final minus m times v initial, right? Now, we know that the v final obviously is going to have to be that the mass stays the same for all of this. That's 1.2 times 10 to the power of 3, right? So 1.2 times 10 to the power of 3 kilograms, right? Our v final is actually 0 meters per second, and we're gonna have to subtract this from 1.2 times 10 to the power of 3 kilograms times our v initial, which is 25 meters per second, right? And if you actually plug this into your calculator and you subtract these two values, you get that J is equal to negative 30,000 newtons, right? Which means that you need to apply an impulse of negative 30,000 newtons or 30,000 newtons to the west, right? Because it's traveling to the east to slow it down, right? So that's going to be your answer. And number 65 says, what is state the direction of the impulse? Well, if 25 meters per second, which is a positive value, means that it's traveling to the east, a negative value of n, or a negative impulse, means that it's the opposite direction, right? So if we're traveling to the east, and what's the opposite of east? It has to be west, right? So that's all. Moving on to number 66 to 67. It says that the diagram shows a negatively charged oil drop that is suspended motionless between the two oppositely charged parallel horizontal metal plates. The electric field strength between the charged plates is 4.0 times 10 to the power of 4 newtons per coulomb. The 1.96 times 10 to the power negative 15 kilogram oil drop is being acted upon by gravitational force F, and the electric force F of E. Calculate the magnitude of the gravitational force F of G acting on the oil drop, right? Show all work, including substitution with units, whatever. So it's asking us for the gravitational force F of G, right? If we go into our reference table, it's getting a bit cluttered up, so I'm just going to delete it, right? It's right here, it's saying that F of G, obviously we're not going to use this because we don't know the mass of these two plates, right? We don't know the mass of these two plates. We only know the mass of the oil drops. So we don't have M1. We don't have an M2, right? What we do have, right, is the mass of it, right? What we do have is gravity, and what we're asking for is F of G, right? So literally, we're just going to write F of G is equal to, or sorry, rather, we're going to write that G is equal to F of G over M, right? We're going to rewrite this as F of G is equal to G times M, right? Because they're asking us for the force of gravity, right? F of G, or F sub G. And now we're just going to have to plug in our values, right? We have F of G is equal to 1.96 times 10 to the negative 15 kilograms times 9.81 meters per second squared. And if you plug it into your calculator, you get 1.92 times 10 to the power of negative 14 newtons, right? So that's all you need. Now, 68, what 68 is asking us for is determine the magnitude of the upward electrical force acting on the oil drop suspended motionless between the charged plates, right? Before you even start looking for your formula, right? Think about what they just said. The oil drop is suspended and it's motionless, right? It's suspended and it's motionless. Now, what's happening is that it's being pulled down, right? The force of gravity, we just said, it's being pulled down by 1.92 times 10 to the negative 14 newtons, right? Right? And if it's being pulled down by that, obviously it's going to be moving. So we need something to balance that out. We need something to cancel that out. So obviously there's going to be an electric force that's equal to that, which is 1.92 times 10 to the power of negative 14 newtons, right? Think about it. If I have a box, right, and I have a rope, and I'm pulling this rope down by 5 newtons, and someone else is pulling this rope up by 5 newtons, what's going to happen to that box? That box isn't going to move because there's an equal amount of force on both sides. Same thing goes here. If this is being pulled down by this amount of force, I need to pull it up by the same amount of force in order for it to not move a single bit. So really, my answer here is going to be the exact same answer to my previous question. That's all. It already gives me the units, right? So number 69 through 70 says calculate the net electric charge on the oil drop in coulombs. You have to show your work and substitution, right? So what I just solved for is F of E, right? So I have FE. What I also have is I have the electric field strength, right? They give me electric field strength, which is the same thing as just saying E, right? Electric field strength. And now they're asking me for the electric charge in coulombs, which is just Q, right? So I have FE and I'm trying to solve for Q, right? So if I go into my reference table right here, I go to energy or electricity, right? F literally right here is the formula that we have to use. It's E is equal to FE divided by Q, right? So here I'm going to write E is equal to FE divided by Q, right? When we're solving for Q, let's just put this in terms of Q. That means that Q is equal to FE over E. Next, all I have to do is just substitution with units, right? Q is equal to 1.92 times 10 to the power of negative 14 newtons divided by 4.0 times 10 to the power of 4 newtons per coulombs, right? That's the electric field strength that they told me up here. And if I plug this into my calculator, I get Q is equal to 4.8 times 10 to the power of negative 19 coulombs, right? So that's all we had to do for that one. Moving on to number 71 to 72. It says that in a circuit of 100 ohm resistor and a 200 ohm resistor are connected in parallel to a 10 volt battery. Calculate the equivalent resistance of the circuit, right? So we know that they're connected in parallel, and we're trying to find the equivalent resistance. If you don't know this formula, scroll down, parallel circuits, boom, that's going to be your resistance. So I'm just going to write 1 over Req is equal to 1 over R1 plus 1 over R2, right? Because we only have two resistors that are connected, right? That's all I need to do, right? Then I could write Req, oh, wait, almost messed up. Now I need a substitution with units, right? So 1 over Req is equal to 1 over our first resistor, which is 100 ohms, plus 1 over our second resistor, which is 200 ohms, right? And now I could write Req. I plug this into your calculator, solve for Req. I get Req, or the equivalent resistance, is equal to 66.67 ohms, right? And that's with units, so that gives me full credits. Moving on to 73 to 74, it says calculate the current in the 200 ohm resistor, right? So what I'm given is I'm given voltage, right? And I'm given resistance. Now I'm just trying to find current, right? Now I could use the formula V equals, R equals V over I, right? R equals V over I. And since I'm trying to find the current, which is equal to I could just rewrite this as I is equal to V over R, right? Then substitute with units. I get I is equal to 10 volts over 200 ohms, right? Because it's asking us the current in the 200 ohm resistor, so it's specific to that one. And if you solve for this, you get I is equal to 0.05 amps. Great. So now it's saying determine the power dissipated by the 100 ohm resistor, right? So if you don't know what power is, you could look here. You know that P, if I could find it. Oh my god, it happens to me every single time. P, electrical power, right? Power. And that's power dissipated, right? We don't know how much over how much time, right? But just power dissipated. And here's the formula, right? 100 ohm resistor. So, and we're given ohms, and we know that in a parallel circuit, right? We have a voltage which is always constant, so I'm gonna use my voltage that they give me here. So here's 10 volts, right? So I have 100 ohms and 10 volts, and I'm just gonna plug this into my formula, right? Which is P equals V squared over R, but V squared is 100, and divided by R, which is 100. So my power dissipated is just gonna be 1 watt. That's all, right? So moving on to number 76 through 77, it's saying that a wave traveling through a uniform medium has an amplitude of 0.2 meters, right? So 0.2 meters. And a wavelength of 0.4 meters and a frequency of 10 hertz, right? So on a grid, complete one cycle of the wave, right? So really all you need to do is just graph this. We know that it has an amplitude of 20 meters, right? So that means it's going to rise and it's going to descend by 20 meters, right? That's one. Now the next thing that we know, sorry, wrong page, is that it has a wavelength of 40 meters. So the wavelength means that it's going to go all the way up and it's going to go all the way down within 40 meters, right? Within 40 meters. So it's going to stop there. And frequency really doesn't matter, right? So all we're going to have to do is draw a graph that completes one cycle in 40 meters. And that's what that means is it's going to rise 1, it's going to descend 2, it's going to rise again, or rather, sorry, it doesn't touch 20, right? So here, this is all literally how it's going to look like, right? It's going to rise to 1, then it's going to drop, then it's going to continue dropping, and it's going to rise back, right? And you can curve these edges out, but really, this is all that they're looking for, right? The amplitude is going to be 20, right? The distance between this point and this point, right, is going to be 40. That's all they're asking for. That is one complete cycle of the graph, right? So number 78 to 79 says calculate the speed of the wave. So all you're gonna have to do here, if you don't know the formula for the speed of the wave, it's v is equal to lambda times frequency, right? So we know that the wavelength, it already told us that's 0.40 meters, right? Then our frequency is 10 hertz. So now we have velocity is equal to 4 meters per second, right? Number 80 says determine the period of this wave. If we go ahead and we look at our reference sheet for waves, we know that t is equal to 1 over f, right? Obviously, we don't need to show work for this because it just says determine. Well, if t is our period and 1 over f, just literally substitute units, right? T is equal to 1 over 10 hertz. That means that the period, the period is 0.10 seconds, right? Or 0.1 second. Moving on to number 81 through 83, it says in an experiment, the potential difference applied, blah, blah, blah. Gives us a table and it says mark an appropriate scale on the axis labeled current A, right? So given this axis, right, find a scale or find like a progression of numbers that makes sense, right? So let's just see, this goes 1, 2, 3, 4, 5, right? So the space between each one of these is 5. So does that make sense, right? If I make all of these increasing by 5, would that make sense? Well, let's just try it out, right? So this value is 0.0032. So obviously I can't use 5. I can't use 0.5, right? That's still too big. I can't use 0.05. That's still too big. I can't use but what I can use is 0.05, right? Because it falls, it's before that. It falls between 0 and that. So what I'm going to use, or what I'm going to try use and see if it works, is 0.005, right? Then I'm going to use 0.010, 0.015, 0.020, right, and 0.025. And when I use that, right, let's just see, everything falls under that interval, right? This starts from 0 and then it ends with 0.025, right? So all of our data is actually in between our interval. That's how we know it's an appropriate scale, right? Everything falls underneath it, right? And if it just like spaced out well enough, right? So that's already 1 point done. Number 2 says plot the data points for the current versus the potential difference. I'm gonna go ahead. I'm gonna go and do that right now, right? So literally just take your points into account. I have it printed out on my table right now. That's why I'm not switching back. If you want to go ahead and you want to skip ahead, by all means, I implore you. I'm just gonna roughly sketch to how I see it on my paper. And this isn't, I'm literally just like just filling it out, right? But that, you should get something like that, right? I know I probably plotted 1 point wrong. I probably plotted a bunch of them wrong, but just to save time, I did it quickly, right? But what you really, on the real test, is what you take these, or well, tomorrow, right? The test is tomorrow. You just literally take your values and you plug it in, right? You don't plug it in, but you just put it in your graph as close as possible, right? So now that I have that done, I have to draw a line of best fit, right? Which is literally just a line that does not connect the points, but goes pretty close to every single point, right? So I don't have a ruler on me, but in real life, right, I'd have a line that like is straight and has an equal amount of points on top of it as below it, right? And it's okay if it goes through the point, but what's not okay is for you to draw a line that goes like this, then go like this, then like that, then like that, then like that. That's not okay, right? You're not connecting the point. You're drawing a straight line that goes through as many points as you can go, or travels as close to as many points as you can make it go or travel travel close to, right? So let's be good enough. Like you have like 1 above it, 2 above it, you have 1 below it, so it's an equal number of them above and below, and it also goes through some. So that'd be a good line of best fit, right? And number 84 to 85 says using your graph calculate the resistance of the resistor, right? So it can't get any simpler or any easier than this. Literally, R is equal to V over I, and they tell you R and they tell you I. So just scroll down to where you have space and just type in or write in R equals V over I and use one of these spaces. I'm just going to use 9 and 0.0177 and just go that, right? So literally all you have to do is R is equal to 9 over 0.0177. R is equal to 5, oh, whoa, units, almost messed up here. Right, and now all I have to do is 5.08.47 ohms is what you get for that, right? And that's all answers completed. If you don't want to use your table, right, make sure that you use a point that your line of best fit intersects, right? So let's just say that this is a good point that it intersects, right? It intersects like 0.009 and 4, right? You could use that point. You just have to signify that hey, I'm using this point on my graph that my line of best fit intersects, right? So that's all short answer questions for this test done in about 35 minutes. If you would like more reviews like this, please let me know in the comments. If you like what you saw, please leave a like. If you have any questions, please leave them in the comments. That being said, I wish you all luck. I wish you luck to those of you who are taking it tomorrow, and I hope you learned something. So goodbye.